All right, welcome back. Nature and Code, we're in chapter 3. And in the previous video, we just developed a mathematical intuition for the reduction in genetic variation. And so in this video, what we're going to do is we're going to get another insight out of this really simple equation that you see here on the screen, which is that the genetic variation in the next generation is this term times the genetic variation in this generation. And so because this value is always smaller than 1, we've established that genetic variation will always decrease as an effect of genetic drift. And also, if you look at the formula, it's easy to see that the larger n is, the smaller the effect, or vice versa. The smaller n, so the smaller the population, the larger the effect of genetic drift. Now, I promised in the previous video that there's another insight, and I would like to develop that now. So if we take this formula and we start at an initial value of H0, we have a population at the very beginning, and we're just going to call the genetic variance here H0. I'm just going to start counting at 0. So we know that in the next generation, H1, so that's the genetic variance in the next generation, is going to be 1 minus 1 over 2n times this value. So we can ask ourselves, okay, what's going to happen then in the next generation, at generation 2? Well, of course, it's going to be the exact same thing. It's 1 minus 1 over 2n times what we had before, and before we had h1. However, I've just established what h1 is here, so I can express that in terms of h0 as well. So I'm just going to get rid of h1 here, and I'm basically just going to replace this version of h1 here. 1 minus 1 over 2n times ho. So I'm going to do this one more time, and then I'm sure you'll see the pattern. So in generation 3, we know it's going to be 1 minus 1 over 2n times what we had in generation 2. Now again, we've just established what h2 is here as an expression of h0. And so again, I'm just going to replace h2 with this whole term here. So 1 minus 1 over 2n times 1 minus 1 over 2n times ho. And so on. So you get the idea here, right? At any time point, if you want to know the genetic variation at any time point, t, you just have to multiply this term here, t times, and then times h0. So the more generic expression here is, okay, h at generation t, whatever t is simply going to be this terms multiplied t times, so to the power of t times h0. And that is also an important equation. And so what this tells you, of course, is that as t goes to infinity, or just goes very large, this term will go to 0, because you're multiplying a number that's smaller than 1, between 0 and 1, with itself many times, and that will eventually approach 0. And so whatever value of your genetic variance you start with, after a sufficient amount of time, this value will be 0. So genetic drift will always destroy all genetic variation. Unless, of course, there's another process that counters it, and that's kind of foreshadowing what we're going to talk about in the next chapter when we introduce mutation. But in the absence of such a force, genetic drift and randomness, all it would do is it would simply destroy all genetic variance there is in the world. Now, that is actually not the insight that I mentioned here, because you could have guessed that from this formula. What I want, I mean, it's still, I think, a pretty deep insight, but nevertheless, this is not fundamentally new. The insight that I would like to develop here is, well, okay, so drift destroys all the genetic variation. Fine, let's accept that. How long is it going to take? And one way to answer the question, how long does a process take, specifically a process of decay, is something you might have heard of in the context of chemistry or in the context of physics, and that's that of a half-time. So basically you're asking, okay, given that I start with a given quantity, with a certain quantity, and it decays over time, how much time is it going to take for that quantity to decay in half? Because that gives you a good measure of how fast a process is. And we can express that in a mathematical notation by saying, well, okay, I'm interested in this quantity of h that I have sometime down the road, and I want it to be exactly half of what I had in the beginning. So H0 is what I had in the beginning divided by 2. When is that equality going to be true? So at which point will the genetic variance be exactly half of what it was in the very beginning? So we can now solve this for t. And so I know what ht is, right? We just developed the formula for this. Ht is simply 1 minus 1 over 2n to the power of t times h0. And so now we can get rid of h0 on both sides, because we have h0 here on both sides. I'm going to get rid of h0 here. I'm going to get rid of it here, in which case, of course, I have to replace it with a 1. All right, and now we have a t in the exponent here. That's a bit ugly, so let's take that down. You take an exponent down by taking the logarithm of the expression. So I'm going to just take the natural logarithm. So the logarithm allows me here to bring that t down from the exponent, but then I have to put this term here into the I have to take the logarithm of this term, and consequently I also have to take the logarithm of this term. All right, so that's essentially as far as we would get with just regular algebra. However, we can go a little further if we're willing to make some simplifying approximations. And one approximation that's really helpful here is the following approximation. I'm going to write this here. If you have a number that's very close to 1, so you have something that's very close to 1, and close to 1 here would be x. So 1 plus x. Then it turns out that the natural logarithm of that is in fact approximately the logarithm, is approximately x. Okay, so if you have a number that's close to 1, the extent to which it is actually close to 1, which is x, equals the logarithm of this number that's close to 1. And so if you don't believe me, let's check. I hope you know, right, that Google is essentially a giant calculator as well. So you can say things like ln 1.1, enter, and it will tell you in the calculator exactly what it is. And so here you can see this is 0.09 something something. So 1 plus x here, x in our case would be 0.1. It's quite close. Let's get a little closer to 1. So let's say we want to know the logarithm of 1.01. Now that's already very close to 0.01. And so on. I mean, if you go one step further, now it's even closer. So as you approach 1, it will be the perfect. It will not be an approximation anymore. But so you can use this approximation, especially as long as x is small, and it's a correct approximation. All right, so what we have here, our x here in this case is this minus 1 over 2n. So essentially what I'm saying here is that we can replace that by just saying minus 1 over 2n times t. So I just replace this ln 1 minus 1 over 2n with minus 1 over 2n. So in this case, right, this is the x, and so I can just write x instead of this whole term here. And I just have to be careful to make sure we're now in the world of approximations. It's not exact anymore, but it's good enough. Okay, something else you might remember from your days back in math, ln of 1 over something equals minus the ln of that something, or in other words, the logarithm of 1 over x is, and this is now exact, it is truly the negative logarithm of x. Okay, so consequently I could just write here minus 2, or rather ln, of course, minus ln, excuse me, minus ln of 2, we still have the approximation, is minus, and I'm just going to put the t up here, t over 2n. So what I'm going to do now is I'm just going to scroll down here a little bit. I'm going to multiply both sides here with minus 2n. So what that means is here, over here, I'll get ln 2 times 2n, and over here I get t. And so ln 2, if you the natural logarithm of 2 is approximately 0.7. Okay, so 0.7 times 2 is 0.4, and there we have it. So t is about 1.4 times n. So this is how long it takes to reduce your genetic variation by half. What that means is, we just talked about how genetic drift is this force that reduces genetic variation in populations, and it will eventually, in the absence of any other process, get rid of all the genetic variation that we have. And that's true. However, we've now just established that it actually takes quite a long time. I mean, imagine you have a population of, I don't know, 10,000 individuals. So yes, over time, absent any other force, genetic variation would reduce all the genetic variance in that population. However, it will take 1.4 times this, so it will take, well, I should say approximately 14,000 generations to just have the genetic variance, and then another 14,000 to have it again, and another 14,000 to have it again. Or, you know, in another example, I mean, assume that you have a population of 1 million individuals. Well, it would take a very long time. It would take 1.4 million generations to even have genetic variation. And so the major insight here is that the process is generally slow. But again, you can see here that it is faster when n is small. But even then, right, keep in mind, we were, you know, back in the earlier videos, for example, when we talked about Hardy-Weinberg, how quickly things happened. Within one generation, the population was in a Hardy-Weinberg equilibrium. Here we're saying, well, it takes, you know, however many thousands or millions of generations or hundreds of generations if n is very small, to just reduce the genetic variation by half. So this is, you know, by and large, a rather slow process, but of course, given enough time, it will still lead to the same outcome, which is the reduction of all genetic variation. Okay, I want to wrap up this video, And I just want to reiterate the three major insights we got from this very simple equation that we developed in the last video. And those three insights are, number one, genetic drift reduces genetic variation, always. That was the first insight. The second insight was that this effect crucially depends on the population size, and it is stronger when populations are smaller. And the third insight we had was that the process is, generally speaking, quite slow. It takes about 1.4 times n generations to reduce the genetic variation by half. So I hope that this really brings home the main message of this brief mathematical excursion, which is you can start from first principles, get very simple equations that give you a very good sort of quantitative handle and very strong insights into a process. I mean, just from this simple equation, we got three fundamental insights into genetic drift or into nature in general. And I think that's quite stunning. In the next videos, we'll leave this mathematical world and we'll go back to simulating things. And the next concept I want to introduce is that of the effective population size. So I'll see you in the next video.